A spring damper mass system is shown in this figure. The spring constant is 1 Newton per meter, the damper constant is 0.2 Newton seconds per meter. The mass is 1 kilogram and original position of the right side of the mass is at 1.5 meter. A horizontal force F of 3 Newton is applied to the mass. The mass was pulled to the right, following the force direction, before retracted to the left due to the damping force and to the right again due to the spring force. The oscillation occurs for a while and the mass stopped moving when the system reaches steady state after around 80 seconds. The position of the right side of the mass is recorded to be 4.25 meter. To change the steady state position of the mass while maintaining the pulling force of 3 Newton, an actuator that can provide dual direction force is added to the spring damper system. A feedback control using PID controller and a position sensor are added to the system as well to ensure precise position control. The new system position control is shown in this figure here. We want to discuss on how position sensor reading is related to the actual position of the right side of the mass. For this task, we set the constant value to 1.5, gain to 0.1, limiter to max 5 and minus 5. Several simulations are done to determine which parameters of PID controller best suited the graph. First simulation is with parameters k equals 1, ti equals infinity and td equals zeros. Stop time is 100 seconds. Blue line represents the position sensor, whereas the green line represents the right side of the mass. We can see that both of this graph shows the same oscillations and both reaches the same time to reach steady state, which is 3.97982 meter at 64 seconds. However, they do not reach the constant value that we set, which are 1.5. Hence, this PID controller does not suit this modeling. For task 2, the desired position for the right side of the mass is set to 3 meter. The PID controller parameters are tested with value k equals 1, ti equals 1 seconds and td equals 0 seconds. Stop time is 150 seconds. Blue line represents the position sensor, and the red line represents the constant value of 3 meter that we want to achieve. The green line represents the force that acted on the modeling. The value of the force at steady state is negative 1.5 Newton, means a pulling force is given to maintain it as desired mass position. The time taken to achieve steady state of the desired position for the right side of the mass is 98.1 seconds at 3.00263 meters. So, another simulation is done with parameters k equals 100, ti equals 10 seconds and td equals 1 seconds with stop time 100 seconds. The position sensor shows better oscillations than with the previous PID parameters. The stop time is elongated to 150 seconds. We can see that the time taken to reach steady state is longer, which is 110.7 seconds at 3 meters. Another simulations is done with PID parameters of k equals 100, ti equals 1 seconds and td equals 1 seconds. Stop time is 100 seconds. The time taken for it to reach steady state of 3 meters is 22.8 seconds, which is the shortest compared to the previous simulations. Hence, we can conclude that the PID parameters of k equals 100, ti equals 1 seconds and td equals 1 seconds is the best compared to the other, since it has the least oscillations occur and has the shortest time for the mass to reach its steady state. To test our hypothesis, the constant value is changed to 8 meters with the same PID parameters. The time taken for it to reach steady state is 12.8 seconds at 8.00079 meters. However, if we tested the constant value with PID parameters of k equals 100, ti equals 10 seconds and td equals 1 seconds, we can see that the time taken to reach its steady state is longer, which is 117.6 seconds.